That's a good spot. All right, Algol signature scheme. So basically, this is like RSA, that you're doing it in reverse, essentially. So here's what we want to do. Alice wants to sign a message M. She is going to generate the same stuff as what she did before, and the public and private information is still totally and completely the same. All the same stuff as what we had before. So Alice is signing a message this time. She's generating P. She's generating a primitive root. She's generating an integer. She's coming up with B. That's G to the A mod P. We've got public information. We've got private information. This is all exactly the same. Just like RSA with the cryptosystem and the signature scheme, all of the parameters were generated the same way. The protocol was just different. It's the same thing here. With the Algol cryptosystem and the Algol signature scheme, all of the parameters are generated the same way. It's just the protocol that's different. Okay? So here's the protocol then. Here's what she's going to do. It's basically stuff backwards. So she wants to sign a message. She is also going to generate K. This one has a little bit more restriction on it than Bob's K previously. So this one needs to have a random integer with the GCD of K and P minus 1 equal to 1. Whenever we have a GCD equal 1, that should ping something on your mathematical cryptography radar. If a GCD of K and P minus 1 is equal to 1, then what can I compute mod P minus 1? What exists? We're used to doing this mod N or mod P, but that's okay. What exists in relation to K mod P minus 1?
Phi of K.
Yes, but not what I'm looking for. Correct,
okay.
But not helpful. What else?
They are relatively prime.
K and P minus 1 are relatively prime. That's totally true. That's another way of saying that, but still doesn't tell me what exists. If K and P minus 1 are relatively prime, then what exists mod P minus 1?
The inverse.
The inverse of, Sarah?
K mod P minus 1.
Absolutely. K inverse mod P minus 1 exists. That's going to show up in just a couple of lines, so that's important. That exists. Okay. She is also going to compute Y. It's going to be G to the K mod P. Y is going to be G to the K mod P. And then here's her signature. Her signature is also an ordered pair in this case. So the first part of her signature is Y. That's what we just computed previously. And then the second part of her signature is M minus A times Y. All of that is times K inverse, and then all of that is mod P minus 1. This is a messy signature scheme. RSA is much simpler to deal with. It's messier. There's messier stuff going on here. So that's going to be her signature. It's once again an ordered pair. We're going to shorthand for M minus A times Y times K inverse mod P minus 1 and call that Z. Okay? So that's the first step in a signature scheme. The first step is signing the message. What is the second step in a signature scheme? What else has to happen? She's going to send the signature off to Bob. And what does Bob have to do? Second step in a signature scheme, Bob needs to
authenticate.
Verify, authenticate. Yep, absolutely. Okay, so here's how Bob is going to verify. He gets the signature Y comma Z, and here's what he's going to do to verify. He is going to compute B to the Y times Y to the Z mod P. He is going to compute that. B to the Y times Y to the Z mod P. That's what he's computing. Let's talk about whether he has enough information to compute that. B is public information, so Bob can compute B, no problem. Y came along in the signature, so that's fine. Z came along in the signature, so that's fine. And P is public information in the system. So Bob has all the information he needs there. And then he's going to compare, and he wants that to be equal to G to the M mod P. So he's going to accept the signature if that has those two matching. Okay. And again, for verifying a signature for the right-hand side, G is public information. So Bob has that, no problem. M is the message. And remember, when we're doing a signature scheme, we always send along both the message and the signature. So although I didn't say it specifically, Alice is going to send M, and she's going to send the ordered pair Y, Z. She's going to send both, because we always send both a signature and a message along. Okay, basic idea? Doing good with the basic idea? Let's talk about why it works, and we'll do some more math here. So why does it work? Looking at what we have, Bob is going to compute that, and hopefully he gets G to the M back out. So I did the first step for you. You guys are going to do the second step for me. Remember what Y is in our signature scheme, and I only replaced it in the second part. Y is G to the K. If you go back a couple of slides, Y is G to the K, so I replaced it in that second one. That's going to be Y. Okay, so this is our first step. What is Z equal to? I'm not sure if this is a good class participation question or not with this format, but that's okay. Z is equal to what? Somebody give me a value of Z. Be brave, volunteer virtually. Daniel, value of Z.
M times B to the K mod P.
Say it again.
M times B to the K mod P. Oh wait, that's something else.
There's an M in there.
Yeah.
M minus A times Y times K inverse.
Yeah. Yep. So we got M minus A times Y times K inverse mod P. Mod P. Okay.
Minus 1.
Yes, M minus A times Y, I'm sorry. M minus A times Y times K inverse. Okay, we multiply exponents. When I multiply exponents there, what do you see with the exponent that I'm multiplying in that second part? Something good happens. What do you see with the exponent in that second part? Cody, say again?
The K's cancel out.
Yeah, the K and the K inverse cancel out. So all I'm left with is M times M minus A to the Y. The K and the K inverse cancel out. That's great. Okay, B is equal to what? Go back to like 4 slides ago and figure out what B is equal to. This is from our regular normal Elgamal. What was B? Somebody give me my value of B. Who hasn't talked yet today? You can do it via chat if you want to. That's okay. Somebody give me a value of B. What's B? Be brave, volunteer. We're working on getting people. Yes, that is G to the A mod P. So we're going to substitute that in, G to the A mod P. And then I'm also going to split that second exponent into 2 pieces. Okay, do you see it? What am I supposed to be getting? In the previous slide, I was supposed to do B to the Y, Y to the Z mod P, and I was comparing that to what? In my previous slide, what was I comparing that to? That was supposed to end up to be, previous slide, that was supposed to end up to be, oh wait, I have a comment, here we go. That was supposed to be G to the M, thank you. Lucas and Cody both G to the M. So, do we see it? Do I get G to the M? Do we see it, multiplying it out? Yes, yes, good. All right, so I can do a couple more steps if I want to, and then I get G to the M, as desired. Yay. Okay. Again, because this is not the greatest format for demonstrating and because I don't have a primitive root, I am not going to walk you through the Perry version of the Elgamal signature scheme. But on this next homework assignment, which I will get posted today, there will be plenty of examples for you to work through, and there'll be a couple for you to work through and execute the Elgamal signature scheme. It's just following a protocol. That's all it is. So figuring out following a protocol. All right, the last slide I am going to skip talking about, but you can read why it's secure. So one of the reasons that this is secure is because of the discrete log problem, and we just talked about that. The other one has to deal with forging a signature, and the information that she needs in order to do that. So you can look at the last couple of slides and see why this is secure. Okay, therein lies our first virtual cryptography class with actual real cryptography content. How are we doing? Is this workable? Are you okay? Is this doable? You're gonna learn things, you'll be able to do the homework. You've gotten it figured out now in terms of if you want the slides up on your screen or on my screen, they will be posted on Moodle before class. Thank you, Elijah. Yes, this is working good. Helpful, doable, it's not ideal. It would be much more ideal for you to be in the classroom, but yes, this is workable. Okay, all right, thank you. Couple of things. So reminders again, all the homework due dates are due in Moodle. Better than nothing, thank you. Yes, we're absolutely going with better than nothing for the rest of the semester. Homework due Friday is the first one. Homework due, I'm not sure when homework 4 will be due, but I'll take a look and get a due date for you, and then tentative dates for the tests. The one other thing I want to talk about before I let you go, and this is why we ended a little bit early, is papers. So Cody emailed this morning, libraries are closed. Yes, indeed, libraries are closed, and the WLC library was open, and now the WLC library is not open anymore. However, you do still, so we're punting the 5 books. If you hadn't started research already, 3 books. If you hadn't started research already and you haven't gotten your books, we are punting on that requirement. But you should still have access to JSTOR on the WLC library page. I'm pretty sure. I haven't looked there yet, but I think that that is still up and running and they've given you remote access. I will also be more lenient for web sources on the paper because you can't get books at this point in time. So please still do double check websites with me that aren't .gov or newspapers or magazines. I'll probably approve them unless it's like Sally sitting in her basement blogging about the Zodiac Killer, which Rachel hasn't sent me, which is good. So double check those with me, but we are, if you can't find books, that's okay. Let me know what's going on, keep me up to date, but we'll make this work. It's not ideal ever, but we'll make it work. Any other questions? And you can either ask them personally